Okay, thank you, Michael, for the introduction. So, can you hear me well? Okay. So, I was planning to use this thing. Is that working properly? Yes. Okay. So, well, I will explain a little bit the contributions that we have done, and in fact, while preparing the talk, I thought, well, that we can go really to the past and see how we started, right? So, a little bit of history. I come from UPC. I'm affiliated both with UPC, Technical University of Catalonia, and PSC. UPC was created in 1971. Then, until 1977, we didn't have the computer science faculty. So, FIP, this is Facultat d'Informàtica de Barcelona, was created in 1977, and these days we are celebrating the 40 years anniversary. Okay. A year later, Thomas Lang came, and with Mateo they funded the DAC, the Computer Architecture Department, where I'm teaching. Okay. In 1991, Mateo, Jesus, Eduard created the CEPBA. This is the European Center for Parallelism in Barcelona. It was a center inside UPC. And in 2005, we managed to join a life sciences team and an earth sciences team. We installed Mare Nostrum 1. Okay. The machine was installed in 2004. Okay. And BSc was funded. Okay, BSc is this consortium. It's outside of the university. It is participated by the university. I think university has 14 or 15%. The Spanish ministry has 51%, and the Generalitat de Catalunya has 33% or something like this. Okay, so this is a little bit like the story. There is more story there. This past July, I was attending a JLF meeting in Illinois. And Bill Grubb was presenting like the history of parallel computing in Illinois. Okay, and then I could read there, 1977, David Cook introduced dependency graph. Okay, and I think this is like where everything started. And I can explain a little bit more. One of the PhD students of David Cook was Konstantin Polychronopoulos. Okay. Konstantin met Mateo at some point, and I think they really started the organization of the International Conference in Supercomputing. The first edition was done in Athens, I think. Konstantin proposed nano-threads, okay, and hierarchical task graphs, okay, and we took that idea and we started there the Nanos project. It happens that nano, it's like 10 to the minus 9 or something like this, but in Catalan we say nanos to small children. Okay, so it fits perfectly. So from there we say we have the Nanos library. Okay, it's the library that supports nanothreads, and it's still the library that currently we use in our OmpSs programming model. Okay, and in fact earlier than that, 1989, Eduard and Jesus were already publishing, and if you read the first sentence of the abstract, in this paper we present a new method for extracting the maximum parallelism out of do loops with tight recurrences in a sequential programming language. So, perfectly fit. Okay? So, a little bit of motivation. We like to try to help programmers to get productivity and performance. Okay, so we are proposing this task-based programming model. Okay, OmpSs, with some basic support for tasks, and then we introduced slowly dependencies, priorities, task loops. Okay. We also did some work. Diego Caballero, currently at Intel, did a very good job on the SIMD code generation. We did also support for heterogeneous platforms. I will show you some of the proposals and how the environment is at the end of the presentation. Judith Planas in our group did the support for CUDA, and she's currently in Lausanne, I think. And the idea is getting a good decomposition of the applications, okay, so that we can target coarse-grained parallelism. So here the idea is, let's go for the coarse-grained parallelism, because if you go for very fine-grained, you don't really get performance because of the overhead of management. So coarse-grained. And also what dependent tasks allows is to explore in the future. What would be the parallelism that I can find in this application in the future execution? Okay, in the future means after 3, after 4, after 10 minutes. Okay, so we have this task that is exploring, okay, without having any barriers, any task weights. It's exploring what's there in the future parallelism of the application and pops new tasks out of those. Okay. Okay. So probably you already know the nice Cholesky plot that we generate, okay, when we exploit this tasking from HPC applications. We also support, so we support basically two flavors, okay. This is OmpSs, this is targeting single node, small clusters, heterogeneous machines. Then we have the same kind of approach, task-based, based on big applications for the cloud. Okay, we call it COMS and PyCOMS. Rosa Maria Badia at BSc, my colleague there, is leading these efforts more on the side of cloud, where a task is not really a piece of code, it's really a big application generating some data in a file, and then that file is stored in the cloud, and then another application that depends on that data is started afterwards. So here the dependencies go more on objects and files, and we have more dependencies on memory, on memory locations. Okay. So let's see a little bit the influence of OmpSs on OpenMP, and well, I have to say that the text that I'm showing here was not done in OmpSs. OmpSs is relatively new brand. Okay, so initially we had Nanos, as I was explaining. We had Paraphrase too as our compiler. Okay, and we never, I don't think we ever joined the two terms until 2008 maybe, probably with the development of tasks, where we said, well, this is like a product. Okay, so we merge compiler and runtime system in a single concept. The model is StarSS, which means execution of tasks in a superscalar way, and for the OpenMP single node heterogeneous machines, we call OpenMP superscalar, in brief OmpSs. Okay, so this is not really OmpSs, but I can mention that we started with the Nanos project in 1996. At that time, we had some contacts with the Parallel Computing Forum in Fortran. Okay, and I understand that was the initial flavor of OpenMP. Okay, we got the Nanos project funded. We developed the Nanos library. We published that in eWomp 1999. At that time, we had 3 workshops related to OpenMP, one in the States, one in Europe, one in Japan. Okay, eWomp and Wompat are the European and the American. I don't remember the name of the Japanese version of eWomp. So we developed support for multiple levels of parallelism. We developed NUMA support. Because in the project we had relations with the University of Patras, from where Konstantin was originally. Okay, Dimitris Nikolopoulos did a very nice job on doing this NUMA support. That was done initially on silicon graphics machines with MIPS R10000 or 12000. Okay, processors, so old architectures. Those are currently in our museums. Okay. We did also, Marc Gonzalez, one of my colleagues in Barcelona, did these pipelined executions. Okay, so in loops do the kind of pipeline support, like now we have the do across. Okay, and Alex Duran did this proposal on the auto scheduling clause for loops. Okay, so this is like pre-OmpSs. Okay, and then we did in fact, Alex Duran did the proposal for tasking, and then we did the proposal for task dependencies, and also the task loop, and task priorities, okay? And something is missing here. That's interesting. Because I realized that while we were doing the proposal of tasking, we also were developing the error handling in OpenMP. We did a publication, and afterwards, and that should be written here, I don't know what it is not. Afterwards, cancellation was introduced, okay, in the OpenMP standard also, okay. And then, well, we are proposing task reductions, dependencies on task weights. We participated a lot on the OMPT implementation. And then current trends are multidependences, commutative, dependence on task loops, and things like that. Okay, so I will go a little bit on this. So let's examine the like the tasking model. No, the big change was to introduce the task concept. Okay. So that was introduced in 3.0, and we allow it already nesting of tasks, okay, and then we have the task wait, where a task can wait for their children, okay. Then in OpenMP 3.1 we introduced the final, in order to say, well, this task can be optimized so that we know that it will not generate further tasks, okay. So it's also to implement this cutoff mechanism in order to avoid the creation of too fine-grained tasks, okay. So then we also added the priority, okay, in 4.5, task priorities, okay. So this allows to exploit irregular parallelism from applications that are based on different data structures like trees, graphs, lists, or whatever, and also supports recursion. Some of the experiments that we do with so in task dependencies, okay, so what we do is we express the directionality of the data, okay, so the actual dependencies between the tasks, in fact, are not expressed by the programmer, and I think this is good. So the programmer only says, this task touches this data, uses this data, okay, and then the runtime system computes what are the actual dependencies between the tasks. Because otherwise it will be very difficult to relate all tasks. Having in mind all tasks in the mind of the programmer is complex. Okay. So then tasks are executed as soon as their dependencies are satisfied and there is resources. Okay. If the cores are busy, we execute what's being executed there, and we have the ready queue so that tasks get accumulated there. Okay. So this was introduced in OpenMP 4.0 with the in, out, and inout specification. Okay, I was about to comment about priorities. Some of the experiments that we do are, for instance, try to tune a little bit some of the properties that the concept that we introduce in OpenMP do. So, for instance, in priorities we evaluated if we provide an integer for the value of the priority, what would be the performance that we get in this case from merge sort. Okay, so observe that as soon as we reduce the number of bits of this integer, if we only use 16 bits of like a short value in order to represent the priority, the performance doesn't change. But as soon as we only use 8 bits, the performance really drops, because we are not able to express the full set of priorities that the application would like to have. Okay, and with no priority, there is even less performance achieved. Okay, so this is one of the things that we do, and then we can recommend, well, it would be good that at least a priority could support a range of 16-bit values. Okay, that would be reasonable. So we also participated in the inclusion of task loops. So this is like chunking. So when you have tasks, most of the times you dedicate a lot of effort to change the application. So any loop that you want to parallelize with tasks, you need to split the loop in 2 loops and use tasking in between. Okay, so this is in fact what task loop is doing automatically for you. So it's a kind of productivity for the programmer. Okay, so here we can say how many tasks I want this loop to exploit, or I think it's better to just think on which grain size should have the block. And currently task loop dependencies are still in discussion for 5.0. Okay. So we used the task group functionality in order to propose reductions. The support for reductions is based on task group. Okay, so task group opens the scope for the reduction, and then tasks can just participate in the reduction. Okay, it will be also, and yesterday it was commented, having reductions in task loops. So this is something that it's also on the plans. Okay. One of our proposals, in fact, is trying to relax some of the dependencies, specifically what we call an inout chain, okay, of dependencies. An inout chain is like, I have a set of tasks generating LOI, and then I have another set of tasks that depend on this LOI, and they have an inout on a particular value. Okay, so this means that these T2 tasks will be serialized in this inout chain that you see here. Okay, so those structures are common in applications. Okay, so we suggested to relax that, like using commutative. Okay, which means, well, in fact it's an inout chain, but you can reorder the execution of the tasks. Okay, so as soon as one task is ready to be executed, it can be executed regardless of their relative creation time. Okay, so here you see the difference. Either they go in the serial order, or they go as soon as possible. Okay, and the property that they should accomplish is that the operation they do on this X value is commutative. Okay, so it can be reordered. Okay, this is currently being proposed, I think, and we have another approach, which is the concurrent. So you can say, well, on result I'm trying to use concurrent. Then what the approach here is, the programmer is responsible of the synchronization on that shared variable, because the task in fact in concurrent will run in parallel. Okay, as you can see here, all tasks run in parallel, and then the red line marks like the atomic or critical that you need in order to accumulate, in this case, the result. Okay, I think this is probably more for kind of reduction support. Okay, so it may not be necessary if reduction supports the full thing. Okay, then we can also evaluate the different performance of the two approaches. So this is showing, by the way, our tools are integrated with the Paraver visualizer, the analysis tool that we have also at BSc. So this is a timeline visualization on the x-axis of the activity of the number of threads that we have here. Okay, so this is the implementation of concurrent, and this is the implementation of commutative. Okay, so what you see here is, in concurrent all tasks run in parallel. Okay, and then there is some synchronization inside the task. Here you see the tasks never run in parallel, but they can run on different cores, of course. Okay, because they are just scheduled randomly in the first core that gets the task. Okay, so you see that in this case the commutative is penalizing, because the serial execution is longer than the concurrent. Okay, but there is another property that you can study, which is what is the quality of the execution of those tasks. Okay, and here you see that this window here shows the duration. This time that I'm marking here is the duration of the tasks. The color that you see here is light green, means there is a small number of tasks with this duration. Dark blue, which is right there, right here on top of the pointer, this dark blue means most of the tasks have this duration. So what you see here is that nearly all the tasks have the same duration. Okay, and the duration is short compared to this execution here, where there is more variability on the duration, and the duration is really like double. And you can see here, in fact, that the distance between the arrows, the distance between the green flags that you have in the execution is really much larger than the execution of a single task here. They should be, the code is really very equivalent, they should be of the same duration, but what happens here is that you have the atomic or the critical, probably that was implemented with an atomic, okay, and that synchronization makes the execution time a little, well, considerably longer for all the tasks. Okay, so this is the kind of studies that we can do. Another proposal that we are doing is the multidependences. So what happens here is sometimes applications may have a variable number of dependencies for a task, okay, and if that happens, you cannot write the code with the current approach. Why? Because you would need to write now 7 dependencies, now only 5, now only 1. Okay, so you would need to do a case or a set of if statements. If my dependence number is 7, then I put the directive with the 7 dependencies. If it's 5, I put the 5. Okay, so here we are proposing 2 things. First, to introduce the iterators, okay, which is, well, we should depend on something that is variable, okay, in this case is the length of the list, okay. So these tasks that are being executed here has an inout on L of I, and then I want to execute the full loop here, taking into account all the different inouts, no? So then all these dependencies will go from T1, from the set of tasks of T1 to T2. Okay. Observe that this is in some way also introducing a little bit of regions. Okay, because I'm doing many to one. Okay, it's like overcoming the fact that we cannot have different regions in the memory, in the dependence for OpenMP. Okay, so in this case it would be equivalent to write depend in on L0, L1 and so on until L from to the L size. Okay, so this can be applied, for instance, to applications that have like stencil computations. Okay, so here, depending on where is the position of the block, the green block that I want to compute, if it's in the corner, I have only 4 dependencies. If it's in the boundary, but not in a corner, then I have 6 dependencies. If it's in the center, I have 9 dependencies. Okay, so this is what this code would do. Okay. And this is the execution that we get from a naive like implementation of the application. In fact, this is probably too naive because I can see barriers here, so it's probably not using tasking, but I mean it's a way of showing that if you do just a naive annotation of the application, you get really very a large imbalance of the work. Okay, and this is the same approach but using multi-dependencies, where you can see that we are really solving the issue of the imbalance, because we are breaking a little bit more. We are splitting this execution on these pieces, and they get very well balanced in the different cores. Also here, the execution time that it takes one of the iterations of the application is this size up to here, okay, while the same iteration in the naive annotation is really longer. Okay, so you gain also performance here. Another set of applications that can be annotated is applications like this is a FEM application, so you need to compute on this grid, but you need to take care of which nodes depend on which ones. Okay, so usually in this kind of applications kind of coloring is used. So if you color with the same color the nodes that do not depend on each other, then you can have a set of parallel loops. Okay, so first parallel loop would work on the red ones, yellow, blue, green, whatever, okay? And you can try to do also a kind of grouping using the multidependences, okay? And then here we mix multidependences with commutative, okay? So that as soon as one of the blocks is ready to start, we fire the task that is executing that block, okay? And we can annotate that using commutative and using the range of the multidependences inside the commutative dependence, okay? And this implements a kind of graph like this, okay? And we compare the performance that we got in this application with multidependences, even with the MPI only annotated, so written with the application written in MPI, okay? So this is 512 processes, MPI processes, and at that range we would have 64 or 128 MPI processes with 8 or 4 threads, and you can see that the performance that we get here is even lower than what we get from MPI, okay? So we get some benefit of doing this commutative plus multidependences support, okay? And one of the latest developments that we are doing is the weak dependencies, okay? This is in order to support better nested tasking, okay? So when you have single level tasks, you build a graph which is really fine-grained synchronization between the different tasks, no? The dependencies really can go fine-grained task by task. Sometimes you are interested in having two levels of parallelism, and in this case the box that is enclosing the outer level, okay, don't allow to express some fine-grained dependencies, because the dependencies go from the outer level tasks to the outer level tasks, and from the inner level tasks to the inner level tasks, not across. So here the approach is, well, let's allow dependencies to cross these boundaries, okay? So here like a little bit of advantages and inconvenience, no? In single level tasks you have fine-grained synchronization, okay, less runtime overhead. In nested tasks you are creating more tasks because you need to create the outer level, okay, so you have a little bit more overhead of creation, but it's more like top-down programming model. You can do a step by step, okay? You first go on the coarse grain and then go to the fine grain, okay? You can even search for distant coarse grain parallelism, because the master thread goes and continues without any task wait, okay? But you have this task wait here, okay, and this also introduces overhead and limits the available parallelism, okay? So what we propose is to introduce weak dependencies, okay, in which even if the outer tasks are created, the runtime system manages to build the single level task graph, okay? And we are currently doing experiments on that, and we are finding some applications that are also going well, okay? Now I would like to ask how regarding time?
Another 10 minutes.
10 minutes? Perfect. So I have tried to give you a view of what we do to transfer our proposals to OpenMP, okay? But then I thought, well, I think it's also interesting to see what's the current trends within OmpSs, okay? So let me explain a little bit what we do currently in OmpSs, and I will start showing this schema of our OmpSs toolchain when we want to offload work to the GPU, okay? So specifically for CUDA, okay? So we get the OmpSs application, which has some portions written in CUDA. In this case, we need to provide the CUDA code already inside kernels that are compiled with the NVIDIA compiler, okay? So what Mercurium, the compiler in this case, does is it outlines some specific stubs, okay? These stub CUDA files are generated by Mercurium, and those files are also compiled with the NVIDIA compiler. Then we embed everything as NVIDIA does on a single binary, and we can run the binary, okay? Everything is linked also with nanos, and the host code is just transformed by Mercurium So we can have also parallelism in the cores. So you get parallelism in the cores just by OmpSs directives, and parallelism on the GPU because you have the CUDA kernels. Okay. So the idea is that at execution time we have a set of threads that are running on the cores, and usually you have one representative for GPU. Okay. So tasks can be annotated with target device GPU, and then those tasks, in this case the violet or this color tasks, go to the thread, and the blue tasks go to the cores. Okay. So this allows us to provide different implementations of the same algorithm, either for the CPUs or for the GPU. We do this in this way. So here you see, you have the target device SMP version of a scale task, which is doing a simple operation on a pair of vectors. In fact, the implementation is here. Okay. And then we have the target device CUDA implements a scale task, which is the kernel for the CUDA device. Okay. And as soon as we say that this task implements the former, the SMP version, the runtime system knows that it has two versions that can be selected to be executed given availability of resources, given predicted performance on the different resources. Okay. And in fact we have this versioning scheduling policy in which the runtime system first evaluates the execution of a scale task in SMP. For instance, it executes 3 times the kernel in the SMP, determines performance. It executes the scale task for the CUDA device in the GPU again 3 times. It determines performance, and then it selects afterwards which one is best. Okay. So this would be the implementation of the CUDA kernel, and then at this point a scale task is just invoked in this way. So either the SMP version or the CUDA version, depending on the scheduling policy that we have. Okay. So here the task in fact is this orange task. Okay, which can go in fact either to a core or to the GPU. Okay. So we also have the version for OpenCL, very similar, except that instead of compiling the OpenCL kernels at compile time, we compile the OpenCL kernels at execution time. Okay, so the OpenCL compiler is invoked automatically. You don't need to do anything. You only provide the kernels. Okay, and we have also a version for the FPGAs. Okay, and here I guess I can move. I want to show you one of the developments that we are doing. So this is the result of the European project Axiom. Okay, this board is developed by the Italian company Seco. Okay, and it contains this chip is the Zinc Ultrascale Plus. Okay, so it contains 4 ARM cores, 64 bits, and 1 FPGA. Okay, and we managed to offload tasks using OmpSs on the FPGA of this chip. The ARM cores can also execute part of the application as an SMP device. Okay. In fact, I have the full system running. So if at some point somebody has curiosity, I can give you a small demo of how this works. Okay. So here what we do is, instead of using NVIDIA or OpenCL compiler, we use the Vivado, the Xilinx Vivado tools. Okay. So we also generate a small stub in order to set the interface between the host code and the bit stream that is being generated for the FPGA. And this is just typing make. Okay, so I can have this kind of code, this is matrix multiplication. Okay, we annotate that with the Xilinx HLS directives, like inline, RR partition, pipeline, in order for the HLS tool to optimize the generation of the resources in the bit stream. We currently target 32-bit and 64-bit platforms. This one in the middle is the one that I was showing, and we also plan to work for discrete FPGAs. Okay, and then this matrix multiply function is annotated with OmpSs. So in the same way, device FPGA. I can say here I want this to be device 0 and I want one instance, and this means that I can have here a bit stream configured in the FPGA and I have one multiplication running at a time, or I can just change that to I want this to be device 0 with 2 instances, then I have two IP cores in the FPGA on the same bit stream, and then I can run 2 matrix multiplications at the same time. Okay. One thing that we also have developed is instrumentation from inside the FPGA. Okay, so this is the execution of tasks in the FPGA, and you can see here the submission events that the FPGA is receiving. So new task, new task, new task. The input channel, how the data is transferred to the FPGA, the execution of the particular computation, matrix multiply, and the output of the data back to the host. Okay, so you can see this fine-grained instrumentation, which has been, by the way, very useful. And a little bit of evaluation. This has been just done in the latest days. I'm showing here the evaluation of matrix multiplication. This is running on the 4 threads of the 4 cores of this board. Okay, so ARM cores. We are getting like 2.5 to 11 gigaflops out of the matrix multiplication. Then we have currently 2 bit streams generated. 1 bit stream for the FPGA is of size 128 by 128. Running 100 megahertz. Okay, so you see here that the FPGA is like between 1 and 2 cores in this case. Okay, and then here I'm using the implements approach, where I can also use the parallelism in the cores at the same time as in the FPGA, and we get a little bit more performance. Then we have, this is for different matrix sizes. This is 1024 and this is 2048 matrix size, so they behave mostly the same. Then when we move to a block size doubled size, 256 by 256, and also doubling the megahertz, the frequency in the FPGA, we have a very big increase in performance with respect a single core, okay, and even surpassing 4 cores. So here the FPGA alone is already giving 14.9 gigaflops, I think. When we increase the matrix size, we get 16.5 gigaflops out of the FPGA, and also the implements technique helps, so the cores can still make some help and get better performance up to 24 gigaflops, okay, on this board. And I think here the lesson is, well, these implements in this particular case, where I would say the power of the FPGA is a little better than the performance that you get in the ARM cores. Okay, the implements greatly helps. Okay, because the implements in GPUs, when the GPU is so fast, then the cores really help just a little bit. Okay, not really much. Okay. Okay, so with this I would like to present the conclusions. So I have shown a little bit our experience on parallel programming, how we try to enable productivity and portability, supporting heterogeneous architectures. Okay, our work is publicly available at the Programming Models website, and we will keep working with you in the OpenMP standard, so supporting this kind of different techniques that we are discussing on the face-to-face. Okay, so thank you.
Thank you. Are there any questions? We have time for questions.
Correct.
First of all, I appreciate the work that you do. The forward-looking work is really good. I'm sorry for making out a lot. Talk about OmpSs, how you are addressing new effects for multiple places or cores, and also for multiple devices, like multiple GPUs. Is that something that you're looking at in terms of OmpSs, trying different things? Do you have machines that have that kind of characteristic as a problem?
Yeah, so we have looked at that, and I would say we don't have a conclusion, because we looked at that as scheduling policies. So when we have a NUMA node, we try to use a scheduling policy that takes into account that. Okay, but really I don't have a conclusion there at this point. Okay, sometimes when you do just the plain breadth first scheduling policy, it's good enough. Okay, because
Let me ask it in a different way from a user perspective. Let me ask it differently. When a user gets a more powerful node with more cores or more devices, how does he want to see it? Does he want to see it transparently, or does he want all cloud control? Is there any kind of, from the user perspective, what is it they want to see when they see a more powerful node?
Yeah. So I would say initially he will see it transparently because the program will run. Okay. I would say that he doesn't need to do anything for the cores. The only thing that he needs to do is when you have more GPUs, you need to tell the system, the Nanos runtime, hey, you have 4 GPUs, okay, and then the scheduling is done by Nanos. Then the next step would be, let's try to use the socket scheduling policy and see if this can get a little bit more of performance. But I don't have a solution for that. Okay, so it's still unclear how we can map tasks to the different sockets in an efficient way. One option would be, and we also developed a little bit of this, that following the dependencies, we follow the data. So this task should be scheduled in this node because depends on data that is generated in that node. Okay, but I don't have an application or an implementation that shows good results in that case. Okay.
One more question?
Yeah.
The support for multidependences.
Yeah.
That's part of the field.
Well, I'm not exactly sure what is the discussion at this level, but I think it's ongoing, and we will try to have it for 5.0.
One more quick question? No more questions? Well, thank you, Xavier.
Thank you. Thank you.